In our Gauss's law chapter, we used Gauss's law to find the electric field inside and outside of spheres, insulating and conducting, cylinders, insulating and conducting, and planes, both thick and thin. Likewise, we can use Ampere's law to find the magnetic field inside and outside of a thick wire. Okay, so our job is to find the magnetic field inside and outside of a wire with radius r. Let's draw that on our picture. And we're saying that the wire has uniform current density J. So this is a new expression, current density. Hopefully you remember in our Gauss's law section and our electric field sections, we defined charge density. We had volume charge density rho, which was charge over volume. We had area charge density sigma, which was charge over area. And we had linear charge density lambda, which was charge over length. Here, our charge density has a symbol of J, and it's defined as the current passing through a cross-sectional area of our object. So current over area. Our wire has a circular cross-section, so the current has a label of I, and the area will be pi times r squared. Our current, let's remember, is represented as positive charges moving along the length of our wire. And when you have a thick wire, those charges are uniformly distributed throughout the wire. So they're moving everywhere within the wire. So what we want to do is apply Ampere's law. Ampere's law says we do the integral of B dotted with ds, where S is our path, equals mu naught times the current inside our closed path. Now we need to pick a good Amperian path. A good choice of path would be a circle because it reflects the geometry of our wire. And if we'd like to begin with finding the magnetic field inside the wire, then let's pick our path as a circle inside the wire. So if our path is a circle inside the wire, it means that the radius of our path is less than the radius of the wire. Let's draw that on our picture. It's hard to get a perfect circle, but I'll try and get it close. So there's my radius, little r, and there's my path. Okay, so next, let's remember that the integral of b dot ds, we can show the steps. I won't go through them again because it's pretty boring for you guys to watch me do that, but if this were a test, you would be expected to show those steps. The integral of b dot ds with our circular geometry is the magnitude of b times 2 pi times r. Okay, so that's the left-hand side of our Ampere's equation. What about the right-hand side, our current inside? So for the current inside the wire, this can be a little tricky. The total current in the wire is I. We're picking a cross-section, which is less than the total wire. That means the current inside the cross-sectional area that we picked is going to be less than the total current. To get the total current, you'd have to pick the total wire. We're only taking part of the wire, so we only get part of the current. So I in is a fraction of the total current I. If we want to figure out what is I in, we can use that the current would be the density times the area. The density we defined up above, that's the current divided by the area of the whole wire. So it's the whole current divided by the whole area. And then to get the fraction of current inside the area we picked, we multiply that density by the area of the path we picked, pi r squared. we notice that our pi's cancel and we're left with total current times little radius squared over big radius squared. Okay, that's how much current lies inside of our circular path. Let's go back to our Ampere's law. So the integral of B dot ds equals mu naught times I inside. The integral of B dot ds is B times 2 pi r. Mu naught times I inside is mu naught times the total current I times r squared over r squared. I've got an r on the left and an r squared on the right, so I can divide both sides by r, and I get my magnetic field is equal to mu naught times I over 2 pi times r times little r. So the magnetic field is linear with respect to distance from the center, and that makes sense. Okay, that's our field inside the wire. Next, we'll use Ampere's law to find the magnetic field outside of the wire. If we want to find the field outside of the wire, when we use Ampere's law, we should pick a path that is outside of the wire. We'll pick a circular path so it matches the geometry of our wire. So we'll pick a circle outside of the wire, which means that the radius of our path is going to be bigger than the radius of our wire itself. So our path is out here. Let's write down Ampere's law. The integral of B dot ds equals mu naught times I inside. Let's pick out our two parts that we'll have to fill in. The integral of B dot ds is equal to, and we should show the steps here, the magnitude of the magnetic field times 2 pi r. Our current inside equals all of the current Y because the entire wire is inside of our path we drew. So let's put those two parts together. Our integral of B dot ds is B times 2 pi r. Mu naught is mu naught. I in is the total current I. Solve for the magnetic field and we get B is mu naught I over 2 pi r. So what we see for our result here is that our magnetic field is proportional to 1 over r, and it's exactly the same as a thin wire. So once you're outside, the magnetic field looks exactly the same of a thin wire as a thick wire. Now, because we're physicists, we graph everything. So let's plot the magnetic field as a function of distance r, where r is the distance from the center. So let's see, we can break it into two sections where we have inside the wire and outside the wire. And the crossover point is at the radius of the wire r. Inside the wire, we already found our equation that B was mu naught I over 2 pi r times your distance from the center. It means the magnetic field inside the wire increases linearly. So if we're inside, it's linear. That's because B is proportional to R. At the tip top, at the peak value, that's an interesting point, and we should figure out what that is. That's where we get our max value. And at that point, B is equal to mu naught times I over 2 pi r squared times the value of the distance, which is the radius of the wire, mu naught I over 2 pi r. Interesting to notice, if you plugged in the radius of the wire, capital R, in your equation for the magnetic field outside the wire, you would get the same value, which means it's continuous at the surface, which is a good thing. Okay, once we're outside the wire, we already have our equation. B is mu naught I over 2 pi r. So B falls off as 1 over r. So we get it curving downwards. As r goes to infinity, as r gets really big, the magnetic field goes to 0. So when we're outside, B is proportional to 1 over R, and we get a curve. Okay, so there's a plot of the magnetic field as a function of distance from the center. This example is asking to find the magnetic field in the vicinity of a coaxial cable. Before we get started on this problem, let's make sure you kind of understand what we mean by the coaxial cable, because sometimes looking at these 3D pictures can be hard to imagine. So let's pretend that my pencil is the first part of my cable. And I've got my pencil with my pointy tip pointing this way, so the current in my pencil is going this way. I'm hesitating to say left or right because the camera is all reversed when I'm filming, and who knows how this looks to you guys. So the pointy tip is shows the direction of current. Current is flowing this way. Then what I do is I take the center part of my coaxial cable, my pencil, and I just surround that by some kind of insulator, normally a piece of ceramic. And I'm doing that because the next thing I do is I take another round cylinder. I take another cylinder. Here I've got a glass. I didn't have anything else handier. And that fits over the ceramics. So it looks like this. You've got one conductor right in the middle. That's the pencil. You've got some ceramics around the pencil, and then you've got another conductor on the top. The current in the pencil comes out of this end. So the current in the pencil points this way. The current in the outer cylinder points the opposite way. So that's what this coaxial cable looks like. Coaxial means they share an axis. So there's an inner wire with a current flowing in one direction. Then there's an outer cylinder where the current flows in the other direction. And those two conductors don't touch because they're separated by some sort of ceramic. So that's the setup of our wire. Next, we'll move on and use Ampere's law to find the magnetic fields. Now that we're comfortable with the idea of what a coaxial cable looks like, let's see if we can go ahead and find the magnetic field at the points required. So our coaxial cable has a solid center. It's got radius A and the current flows in the direction shown. It's separated from an outer cylindrical conductor that also carries current I but going in the opposite direction. We first want to find the magnetic field at points outside the central solid conductor, but inside the tube. So before we get to the outer conductor. Let's work on that part first. So for part A, what is the magnetic field between A and B? First thing we'll do is let's draw a path. Okay, I went off a tiny bit there. So that path has radius R, and it's between the two conductors. We'll write down our Ampere's law. The integral of B dot ds. We'll take the orientation of our ds to be the same as the orientation of our magnetic field. So coming around this way so that it's positive is equal to mu naught times the current enclosed by the path. So the integral of B dot ds, we can show that that's equal to B times 2 pi r. Mu naught is our constant. I in refers to the amount of current enclosed by that path that we just drew. That's the current on the inner central solid conductor. That's labeled current I. Okay, let's put these things together. So B dot ds, the integral of B dot ds is B times 2 pi r. That's equal to mu naught times the current inside, which is just I, the current on the wire. So the magnetic field between those two conductors is mu naught I over 2 pi r. That's the same expression as we're used to getting around any long wire. So again, the magnetic field only depends on the current inside. That outer cylinder doesn't affect the magnetic field inside of the space because the current on the outer cylinder is outside. It doesn't impact that inner magnetic field. Next, we'll find the magnetic field outside everything. Part B of our problem now says find the magnetic field outside the tube, so outside everything. Let's draw our path. I'm going to draw a path that has it's a circle, so it matches the symmetry. and it's completely outside of the coaxial cable, outside of all parts. And that's got a radius r. Next, I'm going to write down my Ampere's law. So this is for r greater than c. Ampere's law says that the integral of B dot ds is equal to mu naught times the current inside. Now, the current inside is pretty interesting. The outer cylinder carries current I going in the opposite direction as the current on the inner cylinder. So those have equal magnitudes and opposite direction. The net current is actually zero. That means that the magnetic field outside the coaxial cable is zero. And that's actually one of the attractive features of a coaxial cable. It doesn't generate any external magnetic fields to interfere with any nearby electronics, for example.